We are going to use the mathematical induction in showing that this given expression is an identity, or the equality is true for all n greater than or equal to 1. For those who don't know, this identity is actually telling us that if you're going to add consecutive odd numbers starting from 1, you will have an expression which is a perfect square. 1 plus 3 is 4, so it's a perfect square of 2. We have 3 different terms. 1 plus 3 plus 5 is 9, so 3 squared is also 9, and so on and so forth. This identity talks about that as a sum of consecutive odd numbers starting from 1 is a perfect square. Now, in other references, there are a lot of steps that are introduced in order for us to really prove any identity by mathematical induction, but it all boils down to 3 different steps. The first step is we are going to check whether this identity is true when n is equal to 1. Because if it's not, then there's no need for us to proceed to our second and third steps. So by doing that, we simply look at our left-hand side and take the first term. We have here 1. Okay? And then, as we go to our right-hand side, you look into this expression here and show if this is really true, as you will substitute n equal to 1. And by the way, we chose 1 because that's the smallest possible value as indicated in our identity. So you will have here the square of 1, which is just 1. This shows that our left-hand side is just equal to our right-hand side when n is equal to 1, and we have satisfied the first step. Now that we are done with the first step, let's proceed to our second step. The second step now uses the assumption if we are going to treat n as k. Okay? Because we are going to use that as well in the further parts of our proof. That would mean our given identity, instead of 1 plus 3 plus 5 plus plus the quantity 2n minus 1, as it describes all odd numbers starting from 1 when n is 1, instead of n, we are just going to substitute k for that, and we will have here k minus 1. This is also true with what will happen, with our right-hand side, simply k squared. Okay, as we substitute n for all values of k. Now, before we go to our third step, there is an important note on our second step that we'll be using later, is that here we already acknowledge or probably considered or assume that n, or k in this case, is the largest integer possible. But what if we introduce another integer larger than k? So what is that expression? We are going to introduce another integer k plus 1 larger than k. Just like the next integer larger than 4 is 5. The next integer larger than 112 is 113. So if the larger integer n expressed in this step as k, the next integer larger than that is k plus 1. The point here is, if we are going to introduce that on our identity here, this is what will happen on our left hand side. You'll have 1 plus 3 plus 5 plus plus 2k minus 1. And then, since we are going to introduce k plus 1 as the next integer, don't just add k plus 1 here, because it should follow what is the description of all the terms in that given identity. So it would be like this. Okay, it would be like this. You are going to change k into k plus 1 as you introduce an integer larger than that. So you have plus 2 times your larger integer than k plus 1, and you have here minus 1, which is originally part of your definition in your identity. Okay, so we are adding, unlike the previous video where it's just k plus 1, here we need to use what is really the definition of the terms in that left hand side. Let's not multiply this in the meantime. Let's just stick with that, because to make sure that we are not changing our identity, we are also going to add the same on our right hand side. Our right hand side is expressed as k squared. That's the right hand side, which corresponds to all of this. But then we are adding this on both sides as we introduce an integer k plus 1. So you have here plus, you will have that same expression k plus 1 minus 1. Again, we are not changing the expression, we're just adding same quantities on both sides. Let's note of this in the meantime as our equation asterisk. This will be using that on our next step. Okay, this is still part of step 2. Now, let's proceed to our step 3. We are now going, our step 1 is when n is equal to 1. Our step 2 is when n is equal to k. Our step 3 is when n is equal to k plus 1. As we introduce an integer greater than k plus 1. But different from step 2, as we add both sides, we are now going to substitute k plus 1 on the original right-hand side definition. So instead of, this is our right-hand side, instead of n squared, as described by identity, we are going to change n by k plus 1. So what happens then is you will have here, instead of k squared, you will have the square of k plus 1. Okay? So it's as simple as that. Now, our goal here on mathematical induction is to, let me just make some notations, okay? This is the right-hand side of the third step. Our asterisk earlier was the right-hand side of the second step. To show that this identity is true under mathematical induction, we need to show that the right-hand side on the second step, applying all algebraic processes, will return to an expression equivalent to the right-hand side of the third step. That should be our goal. Okay? So, in short, we're going to manipulate the asterisk and reach this one here. Now, there are some references which will not touch whatever will be the right-hand side of the third step. But just for the purpose of the discussion, let's just take the square of this binomial, and we know it to become k squared plus 2k plus 1. Or if you're not convinced with this, you can always use the FOIL method of k plus 1 and k plus 1. You will get here k squared plus k plus 1. So you still have k squared plus 2k plus 1. Again, there are some references which will no longer manipulate this, just the right-hand side of the second step and reach this one. But for those of us who needs, actual or easier explanation, let me just use this simplified form of this so that it would be easier for us to look some appropriate processes that will allow us to convert or simplify the right-hand side of the second step into that one. So again, we will be simplifying this k squared plus the quantity 2 k plus 1 minus 1, and hopefully we will reach this one here. So let's start by not that one first. Let's try to distribute this 2. You have k squared plus 2k plus 2 minus 1, right? Okay. Then you will have here k squared plus 2k plus 1. And by removing the grouping symbol, the right-hand side of the second step, this was the second step, is k squared plus 2k plus 1, which is just the same with the simplified form of the right-hand side of the third step. And with this, we have shown that our identity earlier is correct under mathematical induction. As mentioned earlier, some of the references will not touch this one here. So what you just simply do is to factor this, and you would know that this is a perfect square trinomial. You'll have the factors of k plus 1 and k plus 1, or you could use the AC way, which will still lead us to the square of k plus 1, still the same as that. But of course, from here, and since you're done simplifying your third step right-hand side, it's easier for us to look at that point, because there are some expressions later that might be difficult in letting the right-hand side of the third step as it is. Okay? We will have more examples as to that. And again, the steps into this is step 1. We assume that n is equal to 1. If it's not, then no need to proceed to the next few steps. But if it is correct, we proceed to the second step with n is equal to k, give an expression in k, and introduce a new integer k plus 1, which will be added, following the definition on both sides of the equations to retain equality. The third step is when we assume k plus 1 for n on our original right-hand side, and then we manipulate our right-hand side of our second step to reach an expression equivalent to the expression, or in a simplified expression, of the third step's right-hand side. Thank you very much for watching.